Damn, it really said recording in progress. All right. Well, that's that. So let me screen share my proper screen. Now, the real question is, do I know which screen is my real screen? I have 4 screens, you see. This one. Everyone see my mouse?
Yeah.
Yep.
I gotta go all the way over here. There we go. This is the midterm. He hasn't given us any other midterms, right? Even though he said he used a different midterm for some questions.
I haven't
No.
seen any new ones.
There's only one.
I'm gonna pull this over here so I can dig without issue. Why am I'm getting spammed tonight. Oh boy. All right. So first order of business. Does anybody have specific areas of interest that they'd like to touch on specifically? Obviously, there are certain problems where, like, you know, given Fourier series, we all know the general method. Okay, somebody just joined and wants in. So we have another person now. Wait, do we? Did it work yet? I admitted somebody. Yeah, all right. I don't know, handle that later. So does anybody have any specific issues? I know, like, we all know the general methods to solve certain things, and we wouldn't really have any luck with trying to guess what he's going to give us. Now, this older midterm is from, I think, 2015, yeah, fall 15. So this is probably more representative of what we'll get than any past midterms of the last couple semesters. Supposedly those were a lot harder due to the remote nature. So we should expect something like this. So Sydney has done very in-depth work on these midterms, and I know a lot of people have also done really in-depth, analysis of these solutions. I think these solutions are well worked out. So if anyone has the time, I recommend you definitely should go through these at least and read through. But like, does anyone have, like, oh, or they have problems with, classical, or, convolution's tricky for them? Or is it just like Fourier series representation stuff? Or do we just want to, like, go through some stuff generally?
I'm up for whatever.
All right. Well, if nobody has any specific issues they want to touch on, then we'll just, try and run through some
Maybe
stuff.
Kramers Rule.
Yeah, sure, bud. Sure, bud. I see. You want to get a 0 on your midterm. I understand. It happens. I'm pretty sure Boykin would legitimately, like, freak out if he sees Kramers Rule. You're getting pushed in the canyon.
I don't even know what you would use that on.
It's for, okay, so he's specifically referring to, I know what this is about. It's for question 1 when you're doing finding the responses. So obviously you can use linear algebra for the ending portion of finding, the responses in classical.
Why?
What do you mean why? Look, it's right here.
Why would you use Kramers?
Well, yeah, the question is, why would you use Kramers? It's stupid. But at the same time, yes, of course, when you're doing matrices stuff, sure. But I think it's, I don't know. I think it's just like he must have run into a group of people, or like a year of students where, like, Kramers Rule was in their DNA for some reason. So if they see, anything that resembles a matrice, they immediately try and
do Kramers. Ugh.
Which I don't even remember how Kramers Rule work. It's like that really weird, like, divide by everything.
Yeah,
but
you
the
divide
thing you're
by, like,
about.
I don't even know.
Yeah, it's good that I forgot it, so I don't even have the urge to do it. As part of today, we're going to try our best and form out stuff that's probably of importance to be on the note card. One of the things we've already mentioned is the absolute and relative difference formulas for.
Yes, those are kind of wacky.
Yes.
Those are a little wacky, and it doesn't look like he gives those to us because he specifically mentions it in question 4 of this exam, but it is not within the possibly useful formula section, as far as I can tell. I don't think any of these are. I think these are all just important relationships. So we'll want those. If someone in the background could be looking over his slides to try and find where that formula specifically is, I'm pretty sure it's.
I can give you the location of them.
Okay, if you tell me where it is, I can open it right now.
It's actually in the solution manual for this midterm. It's just where he does the work for it.
Okay, so that's going to be down here.
It's kind of strange because, like, normally you would think, oh, subtract the.
It's this, right? No, wait, is it this?
It's like last page. There, the bottom in that box. So it's like.
Oh no.
Yeah, it ends up with negative results, which makes no sense.
No, it's that's plus or minus. That's what that means.
Yeah, so it's like you're subtracting the continuous or direct solution with the Parser Walls solution.
Yeah, we'll want to find that somewhere else too. But we'll be making the note card and everything. I recommend, because of how often this stuff's gonna pop up, that everybody has the pertinent imaginary and like Euler formulas down, all the different relationships and tricks that are needed.
Yeah, some
And
good
another
ones to
thing-
have
yeah.
will be
Oh, yeah.
like
Yeah, what are the good ones?
what are they? Where you can convert like e to the plus or minus j n times pi, where you can convert that to just -1 to the power of n. That's
What'd you
another
say there? You said
one.
E.
E to the plus or minus j n pi.
Is
It
equivalent
oscillates
to
between
-1.
1 and 1 and
and-
-1. So it's -1 to the power of n.
That's a good one. Let me see. Do I have my writing
And there's one for
privileges?
pi over 2, but I still haven't fully figured that one out yet.
So you said E to the plus, oh, this is so bad, minus
Yeah,
J.
it's either or on that one.
Is equivalent to -1 to the nth power.
Yep.
So that's a quick one. Now, another big thing that I'm sure actually kind of trips a lot of people up, because I still think it's a little wacky, is the canceling, or I should say like just disappearance of odd and even stuff and when that occurs.
Hmm.
So that's a whole thing we're going to want to talk about here, because he even kind of talks about combining the plus or minus n terms to produce, exponentials into trig functions and so on and so forth. Although from what I've heard, in terms of what I expect on the midterm, there's been a lot of debate, but I still honestly think he's going to give us a classical and a convolution. Because I don't think there's any chance that we just have one or the other, right? Now they might be in the same question. I severely doubt it, but I severely doubt that we'll get like a classical or a convolution. And then the other 3 questions are all Fourier series. I feel like that's a lot of series. Like in this one, he has 2 Fourier series. The only topics we've touched on are classical, convolution, Fourier series, both exponential and trigonometric, which
Well,
means
don't forget the impulse response stuff too.
Yeah.
that's classical.
Not necessarily.
I
Yeah, I
mean,
thought
that's how he
classical is
does.
a little bit different.
That's how he does.
Classical
This,
is a little
isn't it?
bit different.
Okay.
What you're finding there is the shoot, what is it? It's just the impulse response. Classical is
Okay.
basically a replacement for convolution.
Well, yeah, it
Convolution
should
being a
get you the
replacement for
same.
classical.
Oh, I see.
And that's what I was confused about at first, because I'm like, how do you get convolution out of that?
No,
And turns out it's worse than you think, and I just looked it over.
I see. Okay, well then
I can
maybe
tell
it
you
is
what
this
lecture to
case.
go to find how to do classical.
Yeah. What lecture is that?
Let me find it here.
Yeah, I can pull it up really quick. It's probably earlier on.
It's like okay, that's lecture 4. Lecture 4 or 5. What are the dates for these? I didn't put the dates.
It's probably September 7th then?
9/2/21.
The
So
9th?
that's lecture 5. So
Wait,
it'll probably be like
Okay.
9 or 8/28 for lecture 4.
August 31st?
Actually, sorry, no, it's going to be before September 2nd, because September 2nd is Fourier series.
Yeah, convolution shows up in August
Yeah.
31st, so it's got to be like the 26th.
Hmm.
I'm looking around. Impulse response. Did he ever specific? I mean, he had to have called it classical somewhere.
He doesn't directly reference it in class. Like
Oh, my favorite.
I think he writes it on the board at one point, but like he doesn't. It's like very like it's not very noticeable.
Yeah, I have a classical example. It's on the 6th page of my lecture 4, so it should be on like one of the last couple
So
like sets of
in
slides.
this, we have a bunch of impulse response stuff, but down here, I just noticed this though. Where is it? His shift property, which is something he brought up on the midterm. So this
Yeah.
might be a good card topic.
Ugh.
So this is for convolution integral, right? Shift
Yep.
property follows with the convolution integral. So in this case, the shift property, which he mentions right here in the midterm and which he talks about all the time, so it's definitely going to show up. He gives it as a hint here.
Yeah, so basically, I emailed him about that. I don't know. Do we have to use a shift property on the exam, or I don't know.
So
You can do it either way.
you could, and he mentioned that in our first midterm review because someone asked, like, do you have to? And the shift property just makes it easier, from what I can tell.
Yeah,
If you, because it forces you to, it just automatically selects a shift for you, where otherwise, you still have to time shift something, but then it's you have to pick, and you might pick wrong. Because general rule of
Yeah.
thumb is you want to make the easier one to integrate when you shift, so the other thing just comes out of the integral because it's not tau dependent. And then the other thing that becomes tau dependent, you just integrate it, and it should be relatively simple to avoid the all infamous integration by parts poison.
Mhm.
So let's go over here. So the basic shift property is just a 2-line thing. So it starts off with if given the convolution of f1 of t with f2 of t equal to some function, in this case defined c of t, then f1 of t minus capital T1 or tau, whatever you'd rather say there, convolved with f of 2 t minus T2 is equal to c t minus T1 minus T2. That's just a big whole thing. So it just carries through. Now, in general, I don't feel all that bad about convolution. It just gets a little
No.
tricky around those U's. Now, we came about this when we were talking during the first review, and it's definitely going to be a meta to bring multicolored pens to this exam, since he legitimately was like, draw the pictures. So
Yeah.
I guess I'm drawing pictures with funny colors. Same way he does it right here. I'm fine with that. But as you can see, like this convolution example he does is like 8 lines, 10 lines of work. And some of these steps are just for our benefit. In reality, it could all be done in your head relatively quickly. The trickiest thing is always figuring out where those U of T's go and whether or not it pulls out. In most cases, it should pull out to the front. But there's some properties of U of T too. What was it? So there was a link between the delta function and U of T. Wasn't it the derivative of one of them produces the other under the second derivative or something? Does anyone remember that from the first day?
Oh, like the derivative of U of t?
Something. So U of T in a lot of times just comes out of nowhere. And it's not actually, it's because one of the functions has like a d2 squared that results in it because it's like a delta.
All I know is U of t, the derivative of U of t is the delta function.
Yeah, so that's a relationship.
Yeah.
So basically an
Yeah.
infinitely fast spike of energy is what that is.
Yeah, so keep track. That's a quick thing to either remember or slap on your card.
And then, how you get rid of the, so I think in convolution, or is
You
it
said
the,
you said the derivative of U of T is delta.
yes.
Okay.
Yeah.
So ddt U of T is just equal to the delta function. And the
And
reason that's
then-
important though is I believe he said you're not allowed to take the derivative of the delta function. You're not allowed to do that. So whenever you're setting stuff up, like the highest order thing has to produce your U of T. Otherwise, like taking a second derivative would yield a derivative of the delta function, which is a no-go. But I think that's just something we're trained to do implicitly. I don't think we have to think about it.
But then another thing with with the delta function, any function times the delta function is just that function evaluated at 0 times the delta function at t.
Yeah.
That's how you get rid of the delta, I think in the LTI examples.
Yeah.
Yeah, he did
went over
that. He did that.
on the midterm review.
Yeah, I'll open that up. That was our second to most recent one, which means that was our Tuesday. And that was actually a good note because that clears up a lot of where the manipulation
Yeah,
of
it's for the
convolution comes in.
LTI stuff.
Mhm.
I don't know if it's seen on,
I have it
doesn't
up right
seem like
here.
it's seen in convolution because you're not ideally you're not taking the derivative of u of t. That comes out of the integral.
Yeah, he does it right here.
Yeah.
So when you multiply any function, that's the thing. So it's distributive, of course. So when you multiply the delta by anything, it just yields them evaluated at 0, or their parameter becomes 0, I should say. So, and the delta drops out. So this just becomes, so the way I'm writing it on my card, or remembering it, is delta t times f of t equals f of 0. A quick way, just to do it that way. And in this case, because of
0
how,
times delta t.
well, here he has it right here where he has like this whole integral thing, and it's f of t times delta t times f of t, or big F of t times delta t times small f of t. And then this just becomes big F evaluated 0, small f evaluated 0, and delta dissipates.
Huh.
Right here, where where I'm circling with
so-
my-
I am not
In
sure.
the red, right above where you're circling, he talked about how we can just like cross it out and just say it's like right there, that blue.
He says you
He said
can't
you can
omit
cross
it.
that out, and yeah, but I'm saying the blue part right there. He said if you write that,
yeah, that's where it
statement
says.
right there, he said it's fine.
Yeah, you have to be able to. You
So
can't
this
just poof
time,
it.
he says, yeah, but I think
So,
it's
yeah.
because it poofs if the function evaluates to 0, which it does here.
Yeah.
Which is why. Okay, so that's better. So the relationship is then delta t times f of t is equal to f of 0 times delta t. And
Yeah.
you must say it, or he'll get angry, and you don't want him to be angry. So this is the type of stuff that you would see as a part of, why won't my thing just let me touch it? Let's do it this way, and then let me go. Yeah, this is the type of stuff here. So I don't expect too many issues with, this thing. My bet is we're going to get a convolution. If we're not, if it does come down to classical versus convolution, I do believe we'll get a convolution.
Yeah.
I don't think he'll hit us with a classical, but that doesn't mean we don't talk about classical, but convolution is probably bigger. But we have a lot of stuff. So here's a convolution question over here. So does everyone understand? So in this case, he uses time shift property, I believe, right? He did time shift, then no time shift.
Yeah.
Yeah, says it right here.
Uh-huh.
So not using time shift comes down here.
I have a very dumb question on time shift. Does that mean you can just get it in terms of t, and then at the end of whatever your convolution is, you just put whatever the shift was in it initially?
Well, let's see how he does it if he pulls it off. So
Yeah,
he says
I believe
time
so.
shift. Yeah.
It's basically like, oh, I'm not actually going to shift it by t, and then then you put it back in at the end for the certain convolution.
Yeah, it's right here. This is the
Yeah.
full. I mean, the full thing's all the way down here, but this is like the full, like time shift all occurs here. He says it
Mhm.
easiest to use the time shift property, so he shifts it beforehand.
Shifts it beforehand, and when he gets to the end, anytime he sees a t, he puts in what originally was the shift, right?
I think
Where's
so.
where's the answer out there?
Right here.
Yeah, so t
T
minus one.
So he just says t minus 1.
Or you can evaluate it, but your graph is going to be different.
Yeah.
The main thing is your graph's going to be different, so then you'll have a different
So
limit of integration.
He's mentioned time shift a lot, so
Mhm.
odds are it's going to pop up. So as mentioned, so here's a great example of time shift real quick. So he just says easiest to use the time shift property. So he sets his CFT as previously mentioned. If given any two functions convolved with one another, that you can just say, oh, it's going to be equal to some arbitrary function CFT, which is exactly what he says here. We're given this function convolved with this function is equal to CFT. Because of that, we can just say it's going to be CFT minus 1.
Mm-hmm.
Because these functions have no special parameters here. So the formula for this is f of t, f of 1, yeah, f1 of t convolved with f2 of t is equal to c of t, which then via time shift property is equivalent to f1 of t minus t1 convolved with f2 of t minus t2 is equal to c of t minus t1 minus t2. So I'm pretty sure he just stacks those other parameters into a negative 1 here.
You're only shifting the one function, so you don't have to actually subtract
yeah,
it
I
by
see
2.
here.
Yeah. So if it was both of them shifted by -1, then it would be -2 that the final function was shifted by.
I see. All right, perfect.
Yeah.
And then
I need to
luckily
write
for us, convolution is actually rather quick. But as mentioned, unless he explicitly says use the time shift property, you don't necessarily have to, which means you can do it traditionally in the form of I just pick the one to shift. And in this case, looking at these two, in this case, he just we'll just go to the non-shift. He comes down here and he has to pick which one he wants to shift. And it's always just whatever's easiest. I know we're just gonna get something like this with just exponential. Let's see. I hate that this oh, is it because I got a chat? Joseph, in August 31st lecture, he does some problems. Okay, Joseph said something in the chat a little bit back. In August 31st lecture, he does solve some problems using the classical method to show that they're the same. All right, I'm gonna go pull that lecture up, August 31st. This one. Thank you, Joseph. Yoink. So this is the August 31st lecture where it's talking about convolution, but then he does a classical somewhere. So let's see. Same problem,
There it
classical
is.
method right here. Classical is just diffie q, right? If I remember correctly.
Pretty much. I have no idea what he's doing with those.
He's just going,
The
going
three
I
ham.
don't either.
integrals.
What, this?
Yeah.
Let me think about it for a second here. So we're given just some function where normally my immediate thing to do here is just start subbing lambdas in like a freak, but he doesn't want to do that here.
Oh, that's defined as initial conditions. I thought you just assumed those were 0 and 1.
Are they 0 and 1 here?
0 and 10.
Ooh, oof. I doubt we have to
Oh,
do that
gosh.
part.
Hopefully he'll give
I
those
hope
to
not.
us.
Yeah, I think that's far too niche. I think it's just because he didn't give us the initial conditions in the specific convolution problem since they're not necessary or they can be assumed. Oh yeah, let's get the assumptions down. What are the rules for the assumption of the 0 and 1 for the first degree and second degrees for the functions
So
again?
y of 0 plus, I believe, is 0. And then whatever your y of 0 plus that's taken to
The first
that-
power or the
no,
next power?
it's the power that is one lower than whatever it is you're evaluating. So in this case, it's a second order differential equation. So y prime of 0 plus will be 1.
Yeah, and I doubt we're
So
getting
it's
anything
like-
higher than second order, by the way.
Yeah, so everything, every y of 0 plus, other than the one that's the derivative under your order of your normal differential equation, that becomes 1,
All right.
and then the rest are 0. So
Yeah, he does all this stuff and then he does all these responses.
he writes that somewhere.
He's mentioned it before. It's not written here since he did it in some wacky way, but he does show like it's y of 0 plus and then y prime of 0 plus. But
Yeah.
he had to do some wacky solving over here when normally
What
we
did he
just
do
get to
for that
assume it's.
forced response? Oh no.
Yeah.
Yeah, you have to. Oh wait,
This
no,
is
that's
him.
not that bad because you don't
This
have to
is-
do the. It's not a power of t or a
Yeah,
multiple of t.
nothing super horrible around there.
Now there's one that ends up being, there's an interesting property. So if you happen to have your generic solution, like the k e to the minus 3t, you see that?
Hmm.
Yeah, if that e to the minus 3t is in your natural response, you have to multiply yf of t times t. So it'll be kt to the minus 3t. He does that in
Yeah.
one of his examples.
In what slide? Or
Just past
review.
this
Oh, okay. I see.
somewhere.
A lot of.
There, the final classical one right there, I think.
Yeah, we get a
and then
KT
see-
right here.
Yeah, see it? Yeah.
Yeah.
Hype. Although I still stand by my guess that we're getting convolution over classical if he does pick one.
I really hope so.
I feel like even he agrees convolution's better. But who knows how this goes.
I just don't want to have to do both and then see my final answers or don't match.
Oh yeah,
Yeah,
as here's
yeah,
another
that's
quick
gotta be the
thing.
worst thing.
Here's a very important thing
That
to
would be
mention
so
here.
bad.
So this is an exam, like all exams, people get a little nervous for them. Don't do that. Like, do not lock up, do not freeze up. If you are stuck on a problem, just skip it, do the rest, and you either come back and have time to try again, or you don't do the problem. It's better than being stuck on it, not doing the problem, and then losing out on everything else where you could have had full credit. If you're
Right.
spending more than like 3 minutes staring at
Yeah, that's
something,
true.
you move on. You do not keep wasting time. That's a thing I've used to great success by this point. Do not burn time when you do not have it. You know, this is a 4-question exam. It's the standard period, hour and 20 minutes. You know, we get, 30 minutes, what? Yeah, 25 minutes, right? 25 minutes per problem.
Yeah,
We cannot afford to be burning time. So if you
and
if you
each is 10% of your grade.
yeah, so you can't. It's better to lose 10% than lose like 15 or 20% due to a bunch of incomplete or
Yeah.
rushed work. And even then, if you're gonna get stuck, it's probably not at the beginning. If someone's getting stuck at how do I set this up, they were always in deep doo-doo. It's probably gonna be some weird like, oh, I forget this integral, I forget this relationship. That probably won't hit you as hard as missing out on points you could have had because you got locked up and froze up. Particularly, it's gonna be bad here because a lot of people, buy into the hype that this is their doom. And it's truly, I don't believe it's that way. I don't think this is going to actually end up being as bad as it's been foretold. It's going to be hard, of course, but if anything's going to be hard, it's probably going to be the final over this. I think this is all perfectly manageable. Just a quick blur.
Yeah.
But even so, I hate this. This is a midterm.
I mean, he did say that if we do get a convolution on this, he did say that basically to expect a classical for the final.
Yeah, functionally, which is
So.
interesting. So, that's a nice little state of quantum observation. Once they're entangled, once you know one, you know the other. We're chilling. It's just about getting the first one. So Sydney's also made a great observation here, as I'm sure you guys probably have now once I mention it. You notice how for both Fourier series problems, he's got piecewise.
Yes.
He loves piecewise, and I wouldn't be surprised if we see it again like this. So here's some stuff here to mention, I'm sure. So we already have, let's just get back to the Euler's and imaginary relationships. We already have that rather important one that I'm sure will set up, or that I'm sure will show up with regards to positive and negative orders of the E positive or plus minus Jn pi is equal to -1 to the nth power, also known as just an oscillating function. But there's some other ones, quick ones, like what is it? E to the Jn omega t is equal to cosine omega t plus minus, depending on the sign on the J, J sine omega t. Is that right? That's the Euler to sine relationship.
I was not listening.
I will restate it. So if given e to the Jn omega naught t, let's just assume the J is positive for this example, that should be equivalent to cosine of omega naught t plus J. Oh wait, I forgot about the n. I think the n goes inside the cosines. Yeah, cosines. So it should be, sorry, e to the Jn omega naught t should be equivalent to cosine of omega naught nt plus J times sine of omega naught nt.
Yes.
That's the
Pluses
relationship.
and minuses are
carried on the J, and we'll
Yeah.
change that relationship. It'll either be plus sign or minus sign, but that's the switch there. Now it's important to mention that here because he gives you a hint that you can combine these terms and you can turn exponentials into trig functions and vice versa, and that's the method for how you would achieve that kind of stuff. But there's also a little bit of complication with regards to which terms exist and don't exist. If you have a term of the
that's the thing I have the most trouble with.
yeah, it's really wacky.
Yeah.
But we'll also probably want Parser Walls theorem on the page. Does anyone remember it off the top of their head before I have to go to a note sheet for our homework?
It'd probably be easier just to go find the notes on it.
Parser Walls was in homework 6, so I gotta get the homework 6 solution. If this thing would please leave and stop covering my tab. There we go. Bonk. There we go. Parser Walls. Come on. Where are you hiding? Right here. Well, that's about as much as I can think. So this is for the cosine series. That's actually
1/2. What is that 1/2?
Why is there a 1/2 there?
I think that's just because it's only cosines.
I guess it does specify for
Go.
cosine series.
Go to the last midterm review. I believe he has something. He did talk about it there.
He discusses Parser Walls here, but I don't see. Oh, you mean in
No,
the?
I'm talking about like the actual like notes we took in class
Oh, okay,
of the
that would
last
be
midterm.
on the 31st, which I believe I have. No, that's not
Yeah.
it.
So
It shouldn't be the 31st. It should be the 21st, which is this. So let me shift up to the top, make sure I didn't miss it.
no, it's the.
It'll be
Not that one,
28th
is
to
it?
31st, I think.
I'm
or
on the right
30th.
one. I'm on the. Actually,
No,
no, it should be the
go to
next one. It should be
it's the 30th.
Thursday.
It's the 30th.
Yeah.
Yeah, it should be Thursday.
Go to the 30th.
Download that. I'll bring it up in a split second.
Because he did talk about it there. He did talk about Parser Walls theorem, stuff like that.
Yeah, we want the
Scroll down a
general
little
one, and then
more.
we'll go.
Yeah. Should we keep going? Right there. It's
This.
30, but
I think
yeah.
it's this. Parser Walls.
No, it's right under it. But then he has the
This?
2 there because it's both. No. You see the right under that one? Talk about that.
There's the approximate, and then there's the exact. So there's a couple
Yeah.
ones here. So let me pull up my pen. So you're referring to this?
I was referring to the one under it.
This, the full, because it's got both sines and cosines.
Yeah.
Although I feel like that's because the cosine only series in the homework had a half. If it were 2, then it should be 1 instead.
The reason it's 2 is because the magnitude of a sub n squared is equal to the magnitude of a sub minus n squared.
So, okay.
That's why. And I believe that is true for all problems.
So that's just you get to add a 2 there. All
I
right.
believe. If
So
I'm
the
wrong,
formula for
someone correct
Parser
me.
Walls. So his notation is he has a, what is that? A lowercase sigma? Wait, not sigma.
Lowercase what?
What's that? What's the big? What's this?
Epsilon.
Epsilon. Okay. Yeah, he's got-
Epsilon par. Although
epsilon
you can also
par.
call it P sub F.
Yeah.
That's what the book calls it.
Yeah.
So
So epsilon par is equal to the magnitude of a naught squared plus. Now the 2 isn't always the case though, because they're not always equal. That's a special case. The general case should just be plus the sum. And then the augmenting on the sum is based on other external factors. In this case, the 2 comes from a minus n being equal, or the magnitude of a minus n squared being equal to a n squared. Or it's actually both ways. But then the other one is
you would think that would be always true though, since you're taking the magnitude then squaring it.
he did circle it a bunch. So you know what? We'll just say that's the truth.
Let's just-
No.
I don't know.
In class, somebody was asking about it in class. I think it was Elijah. I think he was asking about it in class where the 2 came from or whatever, and that's when he was
I think that was
explaining
like
it.
that was a later part of this.
Was it?
He
Maybe
came
not.
back and it was
know.
like later on the page,
Okay.
and then he came back and was like, "That's where the 2 came from."
Well, let's
Yeah.
see. Let me clear the drawings.
All I know is every problem that I've done.
He
for
keeps
practice,
circling the 2s.
Yeah, every problem that I've done for practice has worked perfectly fine with doing the 2 and then n equals 1 to infinity, or however many.
Okay. We'll
As long
take
as
your,
he, as
we'll
long as
take
he
your
gives
expert
you
opinion.
like, okay, say the first 11 from
Yeah.
-5 to 5.
All right.
Then that's where you can say, okay, let's just go to 1 to 5
And
then
squared.
multiply it by
So the
2.
full formula we're looking at for epsilon Parseval is the magnitude of a naught squared plus 2 times the sum from n equals 1 to infinity, positive infinity, special, you may remember that, of the magnitude squared of a sub n.
Yep.
So that's the juicy Parseval's theorem, and his approximate one down here is not to infinity, it's to whatever the upper bound is here.
What he
Mhm.
asks. And
Gotcha.
if it is a,
So we will denote the previous formula as what? Specific, true, as opposed to approximate, exact.
I think it's called dir.
Screw it,
Direct.
I'm calling that John exact. And then the other one
Whatever.
is going to be, this is just for my own benefit, but I feel like exact versus approximate is a decent enough thing. The approximate version, which we probably will need to do if we need the relative versus absolute difference. I say probably, I know we need to do it, is going to be equal to this plus up to the index. So the only thing that changes is you go up to his requested index of summation, which, by the way, if it's not infinity, I'm fairly certain you either do via your calculator or by hand and just sum everything up, but I don't think it's that nasty. We're allowed a calculator, right?
Yeah.
Yeah, so summing by hand isn't that bad, but if you have a standard TI 83 CE, the summation symbol and its properties exist within the math function. So you can do that way if you
The
prefer.
only issue I can find with that is that if you're trying to sum up like the square of and the square includes imaginary numbers, that's the only thing I can think of.
Fair, but in that case, I would pull the imaginary out of your. You could still, if it's a complex sum, do the rest, and then simply it is a sum. Just add the
Yeah.
imaginary on in your head.
Ideally,
What's it going to
the
be? Negative
imaginary
one.
cancels out when you take
I mean,
the
it should be one or
magnitude
negative.
squared.
It should just be -1, I think, every time.
Actually, he goes into it calculating a sub n magnitude squared.
Right here by hand, he does it all up to the 5th.
Well, left. That's
This.
it's equal to a sub n times a sub n.
Oh, he does the complex conjugate thing.
Yeah,
All my
Yeah.
homies love the complex conjugate.
and then that's when you're.
And here, here's his error thing.
Imaginaries. Yeah.
All right, let's get it. So the error
I've been
absolute.
working on that last problem on the right. I've been working on that for a while, and I still can't. I
This.
have not gotten to what he's gotten to. Yeah.
Yeah, all right. So the error absolute formula is simply the what is that? Approximate versus his direct, as he
Parseval.
calls it.
Yeah, Parseval minus direct.
Direct being this.
No,
being-
direct is the.
No.
He calls
the-
this the direct. But then
No,
why
right
does he
above
do?
it.
Oh, direct is different.
Yeah, the direct
yeah,
is
that's direct.
when you evaluate.
Oh,
it
whack. Okay, well, we got a guy.
integral-wise.
I completely missed that part. So
Yeah.
we're getting direct down too. So I'll call this approximate down here. Approximate. And then we have the direct, which is circled in pink where my cursor currently hovers, is
It
equal
should
to
be-
1 over T naught, which is your period. Hopefully everyone remembers how to find periods of complex signals. I say complex, but they're probably actually not that tricky. Integrated from T0 to whatever, f of T squared dt. So direct is rather simple. You just integrate the f of T, whatever it may be, which may be, who'd have thunk it, a piecewise.
Yep.
Whatever. Well, we'll probably want to talk about some piecewise stuff later on. Also, probably just piecewise like rules. Does everyone feel comfortable with their integration by parts? Because that will be important,
Yeah.
I'm sure. Like not in terms of like doing Fourier series, but like just the process of actually integrating by parts as calculus. Is everyone good with that?
Yep. All good.
All right, good. Because you bet your ass I'm doing some practice for that on my own time. Gotta make sure I can do some juicy integration by parts without missing anything. But in this case, it's just equal to that, which is no issue. Now, integrating along your period is nothing more than integrating from your start to your end of your period, correct? Like when you see the integral
it's all
sign.
just like the period that you care about.
Yeah,
pretty
so when you
much.
see the integral sign with a,
So on this
T
one, it's
naught,
just 0 to 1.
it means you integrate along the point you care for, which
Yeah,
is
because
here.
it's just a unit step.
Yeah.
A really weird unit step.
Yeah, so that's the case. So then let's go back down to where we were doing over here, which is this, the errors. So we have the absolute versus relative. Is that what he says here? ABS, I think, is what he's trying to write as the sub
Yeah,
to the
it's
big boy.
absolute. So it's just like,
So-
what is the difference between your two
So we
values?
have epsilon ABS or absolute is equal to the relative, or no, just the standard Parseval. Standard Parseval function result minus the direct Parseval function result, as denoted by the previous equations, and then the error Was it relative there? Yes, it is relative. Relative error is equal to the absolute error itself. So you need absolute before you can get relative, divided by, once more, the direct result. Now, note that, as you can see here, this can yield a plus or minus. That's nothing more than either being above or below the expected. When it comes to
Ideally, it's a
tolerances,
minus.
yeah, when it comes to tolerances, there shouldn't be any issues there. Just carry whatever sign comes out of that. Don't mind it. Don't pay it any mind. Now, you said you've been doing this one.
Yeah, that one's been troublesome up until the point. Where has it been? Keep scrolling. There on the right, 3:49 p.m. That, yeah. Getting to those solutions has been quite a pain.
Well,
yeah.
this is a good thing to note. He has a lot of wacky magic here. So first things
Even
first,
doing that,
he's
but yeah.
subbing an X, he's subbing in X's by creating a relationship here. And this is nothing more than simplifying what it looks like. You could have just left it if you so desired. But this is, this is a standard change of variables, right?
Mhm.
With this X here, everyone remember how to do just standard change of variable stuff?
Yeah.
You just define a new variable in terms of the previous function, in this case, minus t plus 2, and then change everything about. You can create a little table of all the relevant results. So in this case, you'd evaluate, negative t minus 2 at 2 yields x equals 0 as shown. Same with the x equals 1 part. Evaluate a 1 and you get plus 1 in the x. And then of course that's going to flip the sign because you're integrating backwards. Another thing to note here with respect to just exponential rules is you can decompose exponentials as he does here. And he uses the famous create the -1 to the n that we've written down previously.
Yep.
Here. So he does.
Now, what I don't get is how he flipped his. If you go from that left tile to right, notice he flipped his limits of integration without changing the negative.
No, okay. So so he does actually. So look, I'll note this for you. It's a little. You probably notice it better if you saw the order, but this is all done past. So upon doing your change of variables, you yield a negative.
Oh,
The
minus
negative
Yeah.
is not from doing this. It's not from switching these.
Yeah.
And then when he does switch it, negative goes boop, and then you have positive.
It's
So
like
what
in
do you
that
do?
midterm example, he changed the negative t to s. Do you remember that one?
Let's see.
It was on one of the midterm. Yeah.
Which
It
part?
was.
Was it in 3 or 4? It's probably in 4, right?
I'm not 100% sure.
Well, let's go down to it.
Possibly.
I don't notice a change of variables quite yet.
No, not in that one.
It's in 4 then.
think-
Oh wait,
yeah, I think it was in 4.
sneaky. This
Wait,
popped
or
in
was it?
again. No. He just, we
No,
just see the
it's
relation.
there. It's there. It's in the middle of the page.
What did he do?
Yes, it is. It is in the page.
Oh yeah, he defines
Yeah.
S, doesn't he?
Yeah, so it's kind of like that.
I
So
like
then
how
he
he
ends up
defined
flipping
S
them.
and all he did was flip a
Okay.
sign.
Oh, so all you do to find your DT is you take the derivative. Oh God, I had forgotten that part.
Yeah.
Okay, and that's why he gets to flip it. That's probably why I could never get to his solution then.
Damn, Sydney really be out here forgetting how negative work.
Yeah.
No problems. All right, that's that. So we'll just continue grinding through here. So change of variables is an important strategy to remember. He uses it frequently, and it confuses a lot of people. Whenever you see X's pop up randomly when you thought there were only going to be taus and t's.
Or you
But
can just not do it. That
you
works
can
too.
choose just to not do it. But honestly, sometimes it does simplify. In this case, it actually definitely helps matters because then at the end you just
Yeah.
replug stuff in. It's just another simplification, quick speed. On something where it comes to time saving, it's down to you to decide what you're fastest at.
Mhm.
Because at the end of the day, midterms as opposed to finals are almost always going to be about racing against the clock.
Yeah.
If given enough time to ruminate on a problem, I'm sure most people would, figure their way through it. But, we're in a time scenario here. Finals, you get a little bit more time, but that also most of the time means more questions, harder difficulty, so on and so forth. All right, let's get down the standard formulas for AN, BN, and so forth. Where would those pop up quickly? Probably in the midterm review. Yeah, here it is. All right, A of n and B of n. What's the difference between A of n and B of n again? Is it
B of n's only if you have the
Sines, right?
cosine.
Sonic,
Yeah.
yeah,
cos-
and which we are
yeah.
not going to be using that, I believe you said.
Because he said he wants exponentials.
Yes.
So let's get down A of n then.
Yeah.
Importantly,
It is so much easier to use exponentials.
it took you so long to come around to that.
Yeah, I didn't know the formula for it. I'm like, where's all this coming from?
And then you asked him, and he's like, "It's just there. That's it." And you're like,
Yeah. Oh,
knowledge. All right, so the formula is a little small here, so I'll read it aloud. A of n is equivalent to 1 over your period times the integral over the same period times f of t, that being whatever function you're given, which is why he loves to give these beautiful little piecewises, so you have to do 2 integrals. Even so, times e to the negative j n omega naught t integrated with respect to t dt. So once more, I will circle it with my little marker for the benefit of those watching, in a frenzy, the hour or two before the exam. So there she is. Beautiful. All right.
God, I hope not.
What?
An hour before.
If someone's watching this an hour before, I'm going to tell you now, future whoever you are, I'm sorry.
Yeah.
I'm sorry. I couldn't save you. Even so. Standard calculations here, everything isn't all that tricky to do this part in reality. Like calculating A of n and B of n and all that stuff, we probably won't have to do B of n, thank God, is very basic. And then right here, he also has the full formula for Fourier's, which I also recommend getting down if you don't have memorized. It involves A of n, so you can do 2 things. Now, with regards to notation, when I do Fourier series on my homeworks, I like to write out the whole series if it's not obnoxiously long, which most of the time it isn't. But in this case, I'm fairly confident if you solve for A of n, which you have to, and like circle or underline that somewhere, and then write out the full series later, full series in the form of, with the summation symbol, not summing up to some amounts. I don't think we're going to be asked to sum up the Fourier series or write out a Fourier series to some arbitrary amount. I think we're always going to keep it in summation form. But it's really up to you if you want to rewrite your solution for A of n into the final Fourier series, or leave it as A of n and like right under it solved previously, or draw an arrow to the other solution. Now that's up to you. It could be a time-saving measure, but honestly, in my opinion, I just write it in. I'm sure the A of n solution for this exam is probably going to be something with like, a pi and a pi squared n squared in the denominator and like a single term thing, not super bad. I can definitely see it being similar to one of the homeworks in that respect. Now, the trickiest thing about this is literally with all Fourier series is always this integral. Just integrating, even in exponential, it's always just going to be integrating f of t. And it's because of this, he's going to give us these beautiful piecewises. So is everyone good on their rules of piecewise integration, like how you do this kind of stuff?
Yeah.
Like how, like if given 2 functions, you integrate this one along these dimensions, and then you integrate this one along those. Yeah, so that's not too bad. And then you sum them, correct? You sum them?
Yeah.
Yes.
Yeah.
They are then summed. So you do 2 integrals to become a sum under 2 different limits of integration. That's how you do that. Now, luckily for us, it's not actually that tricky. But the thing is, depending on the function we're given, the integration can get a little nasty. I don't think he needed integration by parts here, did he?
No, there was
Which
none
is
in that one.
awesome. But, we could have a function that's like cosine of omega t times e of negative alpha t minus 1 or something. And then that would involve integration by parts. Now, as mentioned previous, it doesn't seem like anyone explicitly has any issues with integration by parts, which is great. It's not that bad. I do recommend having the formula for it written down if you don't know it off the top of your head. Now, I normally know it off the top of my head quite well, but just in case, let's see what the internet has to say. Thank you, Lamar University. I wanted a formula. You gremlins. This is it.
Yep.
F times g being 2 different functions. In this case, let's just say e of x times cosine of x minus the integral of f prime times g. Now, the thing you want to do here is you want to, based on this, select f to be the thing that disappears. Now, the annoying thing about the one I've been using as an example, cosine of t times e of t, e to the t, is neither of those disappear. They just oscillate forever, which in that case, you have to use that wacky thing from homework 5, where you solve it for like 2 chains in and then set them equal to each other, which is a whole other thing. I don't think that's going to show up. Keep it in the back of your
Hope
mind just in
not.
case. But this is a relatively simple formula, and you just repeat this. So all you need to do is select f to be the thing that disappears. A better example would be cosine of t times x times t squared, let's say. That's a good one. You do integration by parts twice to eventually cause the t to drop out to a 1, and then everything just solves back through. So you'd set f equal to t in that instance for that example. So that's just there. So I'm not going to explicitly say to write this formula down because we might not have to use it, but just in case, keep that in the back of your mind, write it in your card. We have more than enough space in the 5x3 card, which we are allowed to use both sides on, to write down almost everything we've said here, if not all of it, plus more. I
Yeah.
recommend trying to make your handwriting extremely neat and smaller than normal, so you don't have to struggle thinking about what did this idiot write, you know, that kind of thing. That idiot being yourself in the future. Let's see. So that's all A of n. More stuff over here. Yet again, another piecewise. No integration by parts here either. Nope. 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 Change variables. I think so. I see an X came out of nowhere.
Oh,
No,
that's
that
the
was from
formula
a-
he gave you for
Yeah,
integration
he
by
gave us
parts.
formulation.
And I recommend writing
yeah.
that down.
He did a wacky integration by parts one here, but he just gave us the formula for it, so we didn't have to do the whole thing, huh?
Yeah.
So
Thanks.
if we do have
Daddy.
to do integration by parts, hopefully he gives us the formula for that.
Yeah, the quick formula. So I
Now,
was
I
mistaken.
don't actually know where he used that summation thing where it's like pi squared.
That's
over
why
two.
he said possibly useful,
Yeah,
but even so.
yeah.
That,
I actually don't know where he used that.
isn't that the whole, I don't know, I'm not gonna talk. For a second I thought that's the whole, like, you know, summing insert whatever interval to infinity yields like -12 over -1/12 or something. It's like a weird quantum relationship. Oh well. Not important. So convolution stuff we've discussed, shift property, which is important. Nobody's raised any extreme objections. In terms of impulse response and stuff, I think we're all relatively familiar with that at this point and just how to solve it. I mean,
Simple.
there's been enough examples that I think of all things, I feel like most people will perform relatively well on these questions,
Yeah.
if not perfectly.
The only thing I can
These
think
are
of
always the tricky ones, just because, you know, it's just new. So first time we've seen it. So it's just gonna be a little wacky. We got down all Parser Walls theorem stuff. Here he tells you for your direct to go up to 11. But as you can tell here, it's only the odd ones.
no 1, 2, 3.
Oh
4,
yeah,
5.
plus or sorry, I forgot. Yeah, that goes negative and positive, huh? Important note there. 11 terms refers centered around 0, 5 terms in both directions, including 0, all means
Although
11 in total.
I don't believe you can actually use 0 in this case because you end up with a 1 over n squared.
Which is a big fat no-no.
Yeah. Now what's the deal with special cases?
Which ones?
Where like you can have n equals 1,
Yeah.
n equals -1. I remember we did something with that.
On first review, he mentioned a lot of special case stuff.
Yeah.
So that was
It seems like all you do is evaluate it at those values, though.
30th, 28. Yeah,
and
you
just,
have to
say
explicitly.
it.
So where is that? Problem, this says use exponential. Not equal to, okay, it was above here. Have special case. I think the special cases here were 0, which we implicitly solve for at A0.
No, they're j over 4 and minus j over 4, I think.
Well, here he just says this is him doing it generally. So n not equal to 0 or plus or minus 1.
No, there you go. Look, the last ones.
Oh, okay, I see. Oh, because this is what happens. This is him stating what happens when you plug in that n. So you have to, if you have special cases, you have to analyze them separately. how does one find a special case? Let's see. He already found it there, so it's going to be up here. A of n, general formula. The function we're given here is sine. Sine is not part of some special formula. F of t here is sine. He does a change of variables to generate x, so he probably just shifted pi t over tau into an x somewhere. I don't see it explicitly anywhere, but he probably just subbed everything back in later. So he talks about a special case here. So here's his full thing for his A of n, but then he notes that there's a special case because we're going to have some issues where, why can't we put it? He mentioned it in the recording, but I don't remember why he said we can't just use the general formula here. What happens if we plugged in the general with no special sauce?
The only thing I can see is that
Oh,
you've got
it
e to an
drops to-
exponent of n
It drops to,
minus
one of them
n
drops
plus
to 0.
Uh,
Need, since f of something is all reals. I think it, does it approach infinity?
I don't think so.
I'd like to know how he defines those as being special cases.
well, I think so. If you look at the exponential, right, inside you have like negative j pi, then you have like n minus 1.
Mhm.
Mhm.
And so basically, if for that case, right, if n is
The
positive 1,
plus and the
then
minus.
it's going to be 0. So then you'll just be left with
Taus,
the integral
after
from
the-
0 to tau of d of dt, right?
which yields
So
a
then
t.
which then yields 1 over j4,
Yeah.
which is why you
Oh.
got the special cases.
I just
Okay.
don't see why that is an issue to be addressed separately,
I
though.
don't
mean,
either.
I guess look for it. I'm sure it's in the recording, but I just don't remember it. We don't really have the time to go searching for it. I recommend for special cases, everybody go back and watch the recording. Go to the timestamp 3:45. So from when we normally start class at 2:50, that is about an hour into class when we're on this slide. And listen for his special case justification. I'm sure one of us asked for it. Why? It's probably Sydney or Elijah or me. Somebody asked.
mhm.
So we'll just have to confirm that.
I think Elijah asked about where the minus j over 4
where
came
these
from,
come
and
from.
it's just from j being on the bottom.
Yeah, but in this case, actually of that, like once you use whatever method you use to, identify the case, evaluating A of n with your numbers is not hard. It's done
Yeah.
instantaneously. You literally just get to zero stuff out, depending, like you get to zero half of it out, depending on the sign, then you zero the other half out for the other one.
Mhm.
And the thing is here, though, he actually says where he shows that you don't actually need to do the whole other one. In this case, you only needed to do, what is it, -1, because you can do this conjugate rule,
Yeah,
which
Mhm.
just, flips the sign.
since it's purely imaginary.
Magic. All my homies love the imaginary axis. Oh, that's that. So let's go back to this again. Does anyone have any questions on homeworks or anything? Like rules for that? So we've done homeworks on convolution. We've done homeworks on impulse responses. We've done so many Fourier series that my eyes are going to fall out every time I look at them. We all understand.
If we could like find a tried and true method to simplifying those Fourier series, that
What
would
do you mean by
be
simplifying?
getting them to his answers where he's got like, even and odd functions.
Oh yeah, the even and odd
Yeah.
stuff.
Yeah.
Let's go down.
Because I can get it to the not pretty form. And I don't know how much he'd count off if you just left it at that.
I don't
He
know.
does the magic defining n as this, so that he does another type of change of variable in the form of just using these tricks
So
to generate
that's
odds and
if
evens.
yeah. So that's
This happens to
evaluating
generate an odd,
odds.
Mm-hmm.
And then
and
he usually uses 2m if
this
it's
is the
trying to find
even.
evens.
Yeah. So
And by doing that, I
just
don't know
does
what
it.
happens.
This is for his amplitude square, or this is for his alpha squareds. So he can produce this. Beautiful. He describes the odd indices and the even indices. Beautiful.
But then again, I can throw all of that in my calculator for a
Yeah.
summation and it works out perfectly.
I guess a thing to discuss is why the odd and the even indices in this thing become important. Normally, when I think of odd versus even, I think it's because, oh, well, one of those cases is important because it will wipe out like half the stuff.
Right.
But I don't see, like in here, I don't see any signs or anything magic.
See, I would
So
think-
I was working that problem earlier.
Mm.
And basically you do have stuff that goes to 0.
But
Yeah, I
that'll
see
just
those
show
as-
up in your like calculations of the
Yeah, it should show up in calculations, but I don't really know why he
explicitly
wants us
mentions
to-
it.
Yeah, that's what I was trying to figure
Does
out.
he
I
say
mean,
prove that
I
some
don't,
go to
I
0?
don't, all right, let's check. This is problem 4 that we're looking at.
No, I mean,
Here's the thing that I find interesting. He doesn't explicitly, like, he just writes them out and then just doesn't use them again. But maybe, okay, I think maybe it's because look at how different they are. So I guess they both count as their own special general case, where an odd n will have a drastically different representation or a drastically different like thing. But another thing is he just like
now in a computer program that would make sense if you're trying to like
well, yeah, that
make
simplifies
it
it.
more
You
efficient.
just make a switch statement between those representations as
Right.
opposed to brute forcing it every
So
time.
maybe that's why he specifies that, but it's like when
The
we have
the
so
other
limited
interesting
time,
thing here is that he defines it as the a to the odd or the even magnitude squared. That he's
and
not just
just
doing.
to throw us off even more, I know he's done it for even where it's like 4m.
Here's well, yeah, you could define it any way as long as it's
Yes.
even.
Wasn't
That
there?
doesn't
Didn't
matter.
he do Didn't he do an example where like every 4th term is like 0 or something like that?
Some
Maybe that's
probably.
where that came from. I have no
Yeah,
idea.
I'm pretty sure. I'm pretty sure he did an example like that.
Yeah. So here, if for this problem is his general an. So he was able to calculate this Fourier series an almost immediately, and then he has to go down here and generate an squareds, which he does. So this is the
Yeah.
normal an squared, which is right here. But then he goes on to state, need to consider even and odds separately. He just says it. So I guess we just have to consider it. So this is him
Yeah.
calculating for the differences, even though he still just uses like the not here, which is just gonna be, oh no, never mind. He does do, so he does this because I guess it simplifies the indice calculations. So I see why he's doing it, because we have to consider all these indices.
But in the end,
Isn't that supposed to be
You
a
just-
3?
No,
That's supposed to be a 5.
no, because
Yeah. Oh, yeah. M equals 1,
2
0,
times
0, 1,
m
2.
plus
Yeah,
1.
yeah. So it's
So
1,
it'd be
3,
5.
5. I got you. So the M is not. We're looking at what it results after it goes through. So this is for
Yeah.
him calculating the values of the indices to then do his beautiful little sum here and then calculate this. Okay. I guess just consider it, gentlemen. I don't know what else to say. That's just you
but,
must consider
it's
all.
like you
factors.
plug in equals 1,
You
2,
just-
3,
I mean,
4,
it's
5.
really not
It
that-
equals the same thing.
It's not that hard a thing to do. It's just a simple change of variables. I guess just keep it in
It's
your
just
mind.
more error that could. That's the only thing is like
Just
it could
keep it in
cause
your
error.
mind. There's got to be a reason. It's got to be since it wasn't explicitly asked for. I'm sure there's some like it must be faster somehow to have the separate formulas as opposed to
No idea.
I don't know. We'll trust in the work and just assume that it's requested and required in some shape or form. Consider them separately. So we'll call that a special case to consider. In this case, specifically for the Parser Walls relative and direct difference. No,
Yeah.
absolute and direct. It's absolute.
Absolute and
relative, relative
relative.
and absolute difference. So that's
Although
that.
I can vouch for the fact that it does make no difference because I've tested it on my calculator and I get the same values.
Oh well, man. Oh
Yeah.
well.
Nice.
Make
I
the
don't know
funny
if I'm
make
gonna
the
waste time on that.
write the funny wiggles. I don't know what the funny wiggles are needed. They're necessary. Are any of you guys also in 323 besides Sydney?
Yes. I
Epic.
am.
Well, there'll be a session tomorrow where we will be doing examples and such. I gotta
Yeah.
get some
I'll
stuff
be
prepped for
there.
that. That's gonna be epic, bro. I recommend everyone. I don't know how we're gonna pull off the whole we're showing up in class thing. I know he said he'll be there, but I don't know how respondents is gonna like the masks.
Huh.
Oh well.
Hmm.
Oh well. We can all assume like we didn't think of it, even though I'm saying in a recording. Even so.
I think you can like just tell it to heck off whenever it bothers you about it. So
I don't
know.
remember. I don't care. He's right there. He knows we're not cheating. The only reason I'm going is because I don't like being like preemptively thought of as a cheater via those systems. I hate the guilty before innocent thing that we've become. Even so, that's all that. Are there any other questions or stuff anyone would like to touch on beforehand? So we've worked
There's something
through
with the LTI system that I was thinking of, but I can't remember what it was.
we've worked through a bunch of, or I shouldn't say work because we didn't do any
Oh,
examples. We
oh,
did
it's where he
formulas
does
and stuff.
his funky like equivalence things where it's like the
Could
left
you
side of the equation is multiplied by hs of t, which equals the direct delta function.
that
And
let me think. Where would that
I don't know if
pop
we
up?
have to show that or not.
Where would that pop up?
I think we do.
Just to
Where
write
does
it
he
down.
demonstrate that?
Just to write it down and pretend you know what it means.
Does anyone remember where that popped in?
Oh, that's just in the solutions for it for the first one on the exam.
Oh my god, I hate this thing.
Yeah.
Zoom is cringe, let me tell you. There we go. Solutions for the first problem. So he does it here.
Yeah, see it. See where he's got like the left side times h of t equals the delta, and then
This thing.
yeah, and then he gives you your
He just drops h of st out and delta out and just says
yeah,
0.
because y for some reason y of n equals s e of st.
Why do you say for some reason?
I have no idea why. That's why.
From what I can tell, it's almost always that.
It is always that.
Every time he's done it, he always just does this thing where it's this
Yeah,
times.
yeah. No, it's just like I don't know why it is that though.
No one cares.
I,
It
I
is.
normally skip those steps and just get it in
The
terms of
answer
like
is
lambda.
y of n is equal to e of st. If you have a problem with that, go to Zeus or something. He'll solve it for you.
Yeah.
But even so,
I just have written down the way he does those steps.
I do this with lambda because I'm a freak. Even so,
Yeah, that's how I do mine as well. That's how
we had the same
John
diffie
taught
teacher.
it,
That's why we
so-
did it. Yeah. But
and there was no y of n equals e of st.
yeah, so that's relatively, simple sauce. I don't see anything super difficult with that. It's just a little wacky to just know that the h of st just, disappears.
Yeah,
Even though in reality it doesn't. He uses this relation where he just produces a 0 and then a 1 for what is that, his initial conditions, and then just no, never mind. It does just disappear. Oh well. It'd be like
Yeah,
that
because you
sometimes.
divide by e to the st on both sides and it just disappears.
Yeah, it just deletes. It'd be like that sometimes, homies. It happens. Don't question it. Questioning is for after we get A's on our exams.
Exactly.
I'll be so happy if I can just pull an A. If I pulled an A on this, I'm gonna go buy stupid quantities of steak. But if I get a B, I'm still gonna buy stupid quantities of food because I'm happy.
I think
You
you owe
pass.
Mark.
I do owe Mark a steak
You do
dinner.
owe
If
Mark a steak if
I'm
you don't
pretty
make
sure
a
I made a
100.
bet with someone if I don't make an 100 on the midterm, we go get a steak dinner, and it's on my dime. So, oh well, rip me. I scammed myself. All right. Well, anybody else? So how many people? I think there's like a couple of people chilling in here, just listening, being legends. Do you guys have any things you'd like to talk about real quick? This one was more really just a review of what's probably going to be on the exam, what important relationships you should remember. In reality, when it comes to problem working and stuff, that's kind of outside of the scope of what we can do here. The most helpful thing for that is to just sit down and look at the stuff yourself, go open your book and do some extra practice problems, as he stated, is a good idea. But overall, if you're going to focus all your time somewhere, focus it on Fourier series and Fourier series representation. That's most likely going to be 50% of the exam. You can probably fudge your way through LTI systems pretty easily, impulse response pretty easily. Convolution, it really depends on the difficulty of the convolution problem we're given. Odds are it'll be a relatively basic one with just exponentials, 2 exponential functions, probably 2 unit steps tagged onto each one. Know your unit step relationships. Do we have any notes that we'd like to put in our cards with regards to unit step reductions and relationships? We already have one in the form of the derivative of the unit step is equal to the delta function. But do we have any other ones? I know that when you do some time shift stuff, people question why the U of t comes out.
Oh, we need to go, probably something to go over would be the drawings.
How to do drawings.
Yeah.
All right, let's go over to a note sheet where we have some doodles and explain why those happened. Not using time shift.
There you go. That's a
Good
good one.
doodle. So this is not using the shift property on its own. So this is the standard method of convolution where you got to pick the shift. So we have 2 functions here. Where are they? They start up here. 2 functions, h of t being e to the negative parentheses t minus 1 there. No, this is him. Oh, it auto shifted, didn't it? No, it didn't. No, this is just what it's like. This is just what it looks like. All right, good.
Yeah.
He uses the shift property to change it and simplify it.
Mm-hmm.
Even so h of t is equal to e to the negative parentheses t minus 1 times u t minus 1. F of t is equal to e to the negative 3t times u of t. So this is him using time shift to change shit. We're not going to do that. We're going to go down here. So with those 2 functions, we plot. These are just plotting unit steps. That's all these things are. And he mentioned that we're going to want to doodle these out. I don't know if it's for a grade or if it's thing, but just do what he says and make sure you doodle it. So we have 2 cases to always consider with something like this. We have to consider if t is less than the starting condition and if t is greater than the starting condition. And then we map it. So here we have t less than the starting condition based on the initial shift, that being t, or in this case, tau minus 1 here. Up here it is.
Which moves the unit
up,
step to the right.
Yeah, up here it's t
1.
minus 1, but even so, that causes the start condition to shift from the original being 0 over to 1. So you trace 2 unit steps. You trace the unit step of what it is. So in here, we just change the variable t to tau. And then here we do t minus tau.
Yep.
Because we're accounting for tau. This is along the tau axis.
You're accounting for the 2 unit steps that are being multiplied in the integral.
Yeah, so the first one we have
that are underlined.
is a unit step that turns off at t. But in this first one, we're considering t when it's less than. We arbitrarily pick where the t is on this axis between these 2 figures, and we only need to consider 2 options. T being less than the starting condition. Most often, starting condition being 0. This time it's 1 because of the time shift. That's part of it built in, not the shift property, but the time shift built into the first equation h of t being t minus 1.
Yeah, just what he gives you.
Even so. So what happens there is that means that the t minus 1 being h of t turns on at 1. That's what happens here. The other one turning off at t, which is what's represented by the c minus tau because it's red, turns off at t. If t is less than 1, then it turns off before 1 turns on, and you can only consider the unit step to have occurred if both unit steps are on at some same period within a time frame, which is what produces our ever famous hat shape. So in this instance, nothing happens. It turned off before the other one turned on. There's no heartbeat. You flatline. In this one, we're considering t being larger than the starting condition, which once again is 1 in this specific case. So starting condition being 1, this never changes. It's good to note that whatever your starting condition was, which is your u of t that goes on instead of going off, between the figures, it should always go on at the same interval. So you can functionally copy and paste your, in this case, your blue over to both of them, and it doesn't change. Your tau axis never changes and such. Your amplitude also never changes. The amplitude is always going to be 1. Don't mess around with that. It's a unit step. It goes up 1 unit, which is 1. And then here in your red, since t happens after 1, 1 turns on, or blue turns on at 1 and goes on for infinity. Red is on from the beginning and turns off at t. Therefore, we have our famous little hat shape, also known as our single square wave pulse. And that's how you draw the figures. That carries over here. In this one, All he did is use the shift property to recenter our starting condition for the blue back to 0 and normalize it back to what we're used to. If we have to use the time shift property, our figures will look like this, centered on 0. If you don't use the time shift property, our figures will be centered on whatever the starting condition is specified via this. If this were t minus 2, the starting condition would be 2. If it were t minus 0.5, starting condition is 0.5. It's whatever yields this to 0. Whatever produces 0 in the parameter of t is your starting condition. Hence, something of t has a starting condition at 0. If it were just this, if these were both u of t, the starting condition would be, like the shift property shows, 0. And that's just all that is. So all you need to know for figures is, first off, you're moving along the tau axis. You arbitrarily decide where t is, that being first case before your starting condition, and then your second case after the starting condition. Red, or your one that turns off at t, is always going to turn off. It'll start on and turn off. Blue, also known as the one that turns on at your starting condition, will turn on wherever, most likely 0 if it is time shifted, and we don't use the shift property, it will be at whatever thing we stated, which in this case, as mentioned previously a couple times, is 1 for this problem. Are there any questions on drawing these little figures?
I think an important note. So go down to where you have the time shift, where it's shifted over. This is the
time
second
shift.
one.
Yeah, this is the not. This is
Yeah,
the
an important thing to note is that your limits of integration change to where your unit step is, and then what you pull out,
oh yeah, this.
basically the multiplication of those two shifted unit steps, that will be your shifted square wave. So it'll be u of t minus 1,
Yeah, in this time shifted one, it should just be u of t.
because the multiplication of those
Yes.
two results in a square wave between
Over
1
here.
and t of
So
u of
yeah,
t
you
minus 1.
gotta adjust your integrand over here. Up here it should be 0.
That is a very
T.
easy thing to
Down here it's
miss.
1 to t. So you gotta change the rules.
Yeah.
Although if you logic through it, you should recognize integrating anywhere except your funny hat yields nothing. So you shouldn't do it. It's a
right.
waste of time. So just as Sydney mentioned, pay mind to your limits of integration. This is us not using a shift property though. As he said in the midterm with a hint and such, he's probably going to hit us with a shift property, which means you should be normalized and centered on 0 once more, which will yield you with having a special sauce u of t normalized come out as opposed to a shifted. But that's all that does. So spicy sauce there. It's funny figures.
That's all I can think of.
Yeah, I can't think of anything else saucier than that. There are probably a couple more Euler relationships I can't think of off the top of my head. I know there's a couple little ones he likes to
Just
throw.
look up Euler equations on like Google Images, and there'll be one that has the one that you described, and then like cosine in terms of ease.
This is just standard.
Scroll
Where-
down some.
Bonk.
There. Right
Where? This?
now. Shoot.
I mean, when I
Okay,
say the
apparently it's not
standard,
there.
I was thinking of, there's a couple things here.
Yeah.
So there's this one, which I mentioned previous. In this case, functionally anything except I becomes parameter of the cosine and sines. In this case, it's the, but that could very easily be parentheses n omega naught t. And then guess what? Cosine and sine are going to have n omega naught t as their parameter. That I plus whatever the sine of the E is going to be carried over to the I. Sines are only to be considered for the J's, or I should be saying J here, for the J.
Let me see if I can find this
What is this guy
image.
talking about? I get so many random text messages from people. It's obnoxious. We got
Hopefully, I
some.
can't find it.
There's this, which I don't think is useful for us. How is this the most beautiful theory? Get out of my face with that. All right, well, there's a couple of other tiny little ones that I know hover around a bit, but those are probably too niche to be super important to cover here because it'd take far longer to find them than write them down.
Mhm.
Once I have my note card written, I'll post it to the group me. There's no rules about sharing note cards. It's just you must write it yourself, handwritten. not a good schmove to print my note card out because you'll get in trouble for that. If you write down what I put on the note card, there's no issues with that. So as long as you make a hand copy, it should be fine. But
Yeah, I'll send the image of that to
Yeah.
group me as well.
just remember, I'm not responsible if, I don't put a formula or something on a note card and then you need it. I recommend still you try your best to look around for extra formulas. But there's no issue, far as I can tell, with regards to his rules. We're perfectly allowed to share our note cards beforehand as long as everyone's making their own copies by hand. So that's all, on the up and up. So that's that. So if there's no more questions, I have been recording this whole time, right? Yeah, perfect.
Yeah.
All right. I'll post this if anyone ever wants to go back and watch it, but honestly, if you were here already, you're probably fine. I recommend instead looking over old solutions, working some problems, looking at your homeworks too. I know that the averages on most homeworks are rather high. This most recent one was a little bit lackluster compared to the previous, as far as I can tell. I didn't do as well as normal on it. Probably a little tricky. Yeah, that formula that you found.
Mhm. That
Good.
is extremely useful if
Good,
you were.
good note card equations. Hot. That's what I'm talking about.
Awesome.
Yeah, so that, and then I'll post my note card once I'm finished with it. I probably have to go buy some 3x5 note cards. I don't have any.
Or you can just cut them from a piece of paper.
It's too dangerous. I had a teacher in high school who had a rule about note cards, and if he saw you had a piece of paper or a note card that may be slightly larger, he would pull out like precise measuring tools and measure it, and then he'd force you to cut off the excess.
Okay, just don't over measure it.
So once I he had a sub, and he said that as a joke. He wouldn't actually care that much, but he had a sub, and he still had that written in the rules for the test and the sub that day. So the guy comes to me, and I just I'd been using a note card that was larger just because I didn't have any other note cards.
Yeah.
But I had been doing it the whole time and I didn't have any problems with it. So what ended up happening was the guy comes to me and he sees in my note cards, I think an inch larger on the left than everyone else's. And he's like, oh no, you gotta cut it. And I'm like, what? And he gives me a pair of scissors. He's like, you gotta cut it. So I'm sitting there, I'm like, damn, okay. And I had to figure out what to cut. And I had about 10 seconds before the guy would just probably take the whole note card. So I had to sit there and figure out, all right, what formulas don't I need? And I just had to.
No, what you could have done is you could have just cut around all the white space. Just
No. Yeah,
roughly the same area.
I had to stay square or something. I think I
Oh,
had to cut off an edge and use a straight line. So I'm like, damn. So, oh well, good old times. All right, that's everything. So I'll post this. I think this recording's about
It
an
is
hour,
it is definitely useful to work some of his the midterm samples that he did on the last two lectures. That was good to do.
to do those yourself
Mhm.
as opposed to just looking at
Yeah.
solutions.
Mhm.
In general, Fourier series are big. They're gonna be a piecewise, whatever they are. Remember specifically to look over the last two lectures because those are both midterm review topics. As we saw, there's definitely going to be Parser Walls. There's definitely going to be relative and absolute difference that we're going to need. Absolute difference and relative formula has already been covered for Parser Walls, so that's not that big a whoop. But if it comes to the fact where you got to do those odd and even cases, simply remember your variable replacement is n. For odd, it is n is equal to 2m plus 1. For even, it is simply 2m. Now, that's the general. That's what we've been using this whole time. Technically, you could just as easily say, 4m plus 1 or something, but then that would shift your whole thing up. So 2m plus 1 is best for centering around 0. So you produce 1 at the first indice. So just stick with that. Unless a special case says otherwise, such as you need to exclude 1 or something. I doubt we'll have it that specific either. If he's been saying stuff's pretty fair, I don't think we're going to get a lot of special case. Although he did go out of his way to mention a special case in our first midterm review.
Yep. So
keep it in mind just in case.
I don't think anyone really knows specifically what's going to go on here.
For brute force calculating a special case, it's on the slide I'm looking at right now. It's just you use the ANU formula you've come to find, and you just decide what a special case may be. In this case, it's causing zeroing. So you just delete.
Yep.
I think the reason he does a special case here is it produces a simple enough result that it doesn't need to be kept general. If you want to know why, the recording probably says it. Even so, that's probably all for today. So I'll stop the recording, which is done in the Cool Boy.